Good morning, students. So today we have come to the fourth unit in quantum mechanics 1, which is on approximation methods. In the first unit, we looked at some models. Model in the sense, we studied infinite quantum well, finite quantum well, barrier potential. Then these are all for 1D, one-dimension models, and we looked at hydrogen atom, then rigid rotator. So these are all for 3-dimension models. In those models, we calculated the energy eigenvalues, the corresponding wave function, and using exact method. Correct. So that was a problem. We solved Schrodinger wave equation to obtain the wave function and energy eigenvalue with the exact method. We solved Schrodinger equation and we obtain wave function. We obtain energy eigenvalues. So these are all exact methods. So they are all simple systems. Whereas in those models which you are going to look into, they are all complicated systems. So those complicated systems, we cannot solve Schrodinger wave equation. The same approach cannot be followed. We'll have to have some new ideas. So we'll have to have some approximation methods to have approximation solutions. For example, in the approximation methods, we are going to apply some external fields. Light interacts with an atom. For example, just think of light interacts with an atom. We have a spectral line. Okay, for a particular atom, we have a spectral line. Suppose if this system is subjected in the presence of magnetic field, then that line, single line, will split into another 2 lines. So we will obtain 3 lines. So what we call this as a Zeeman effect. Splitting of spectral lines in the presence of a magnetic field is nothing but Zeeman effect. So this is external disturbance, external perturbance. So what we call this as perturbation. So perturbed system. It's a complicated system in which we cannot solve Schrodinger equation here. It's very difficult to solve to obtain wave function and energy eigenvalue. We'll have to go only with the approximation method to get approximation solution. No other way. So this is for the external magnetic field. Similarly, we can go for the external electric field. We have an atom which is subjected to an electric field. What we call this as a Stark effect. So again, splitting of spectral lines. Not only magnetic field and electric field, but also temperature, phonon. So those things are radiations coming out from the outside, from the universe. So those are all perturbation systems, disturbance. They will disturb the system. Okay. So what will happen ultimately? The energy levels of the system will change. In exact method, for example, in linear harmonic oscillator, or square quantum well, infinite quantum well, potential barrier, those models are bound states in which energies will have discrete energy levels. Suppose simpler systems. Suppose we are going to apply any magnetic field or electric field, these level will change. These level will be altered. So we can have some corrections of, so what we call this as first order correction, second order correction, depending on the subject of the field. This field should be very, very, very small. It should be weak fields. Only then this will work out. So very important 1 mark question. External perturbation should be very, very, very small. It should be weak. For the strong fields, this term will disappear. It will go off. So this will have more effect only when the fields are very weak. It's a very less field, small field. Only then this perturbation will work out. So we are going to look into this perturbation system today, and this is for the stationary states. And we are going to have 2 types of perturbation. One is time dependent, another one is time independent perturbation. In this semester, in quantum mechanics 1, we are going to look into only time independent perturbation systems, stationary systems. And in quantum mechanics 2, we will be discussing time dependent perturbation, which is the more reality. Time dependent perturbation is more real. Similarly, approximate methods in which the systems are real. So almost we will have real systems, will have only approximation methods from which we can get approximation solution. Okay, and in the syllabus we will be dealing in quantum mechanics 1, 4th unit. We will be dealing with time independent perturbation theory for non-degenerate case as well for the degenerate case, and we will be studying Stark effect in hydrogen atom. Okay, so there is no Zeeman effect in the new syllabus. We will be studying only Stark effect in hydrogen atom, ground and excited states we will be looking into, then variation method, helium atom. Example for variation method, we are going to study something on helium atom, WKB approximation, Winzel, Kramer, Brillouin approximation. Connection formulae, we are going to have no derivation, then WKB quantization, application to simple harmonic oscillations, a small example. So as I said that there are two systems to solve Schrodinger wave equation. So one is the simplest system. We will be using the Schrodinger wave equation and we will get the exact solution. For example, we used infinite square well, finite square well, potential barrier, hydrogen atom, harmonic oscillator, rigid rotator. So we applied Schrodinger wave equation to obtain energy eigenvalue and the corresponding wave function. So this is the exact method. It's a simpler system. Whereas in complicated systems, in reality, complicated systems alone exist in reality. So we don't use Schrodinger wave equation in the complicated system. We never use. Okay, we will not be using Schrodinger wave equation for the complicated problems. Instead, we will be using some powers. Okay, some perturbation power will be there. That power will be expanded in terms of series. After that, we are going to derive some small expressions. So that will be in terms of expectation values. We will see later. So for example, Zeeman effect. Okay, Stark effect. So they are all real systems. Okay, they are all real systems in which we have two methods. One is time independent perturbation theory, time dependent perturbation theory. In complicated systems, we have two types. Okay, so these are the examples. In complicated systems, we have two types. So time independent perturbation theory and time dependent perturbation theory. In time independent perturbation theory, stationary methods. Then another one will be variation method. Then another one will be WKB method. Okay, in due course, we will be learning all those things. So as I said, Wenzel, Kramer's, Brillouin method. Okay. In time independent perturbation theory, which we are going to have a look into now, and in case there are two cases, one is for a degenerate case, another one is for non-degenerate case. So in the first class, we are going to look into only non-degenerate case. For every wave function, there will be an energy. So this is for non-degenerate case. And variation method, we are going to guess the wave function. So we are going to guess the wave function for the model. For a quantum well, we will have different wave function. For quantum wire, we will have different wave function. For quantum dot, there will be a different wave function. We are going to guess the wave function. And after that, with some parameters, what we call this as variation parameters. So in variation method, we are going to guess the variation function in which some variation parameter will be there. Not only one parameter, it can be two or more parameters will be there. And we are going to differentiate with respect to variation parameter and get the minimum value for the energy. Okay, and thereby the wave function. So that is variation method. And WKB method stands for the semi-classical approach method. So this is when H tends to 0, H bar tends to 0 or H tends to 0, when lambda tends to 0, the quantum mechanical effects will show into classical physics. We know already this one, we discussed earlier. So we are going to use a semi-classical approach to get the energy eigenvalue and the corresponding wave function for all those methods. Okay. So now we are going to look into time independent perturbation theory for a non-degenerate energy levels. So as I said, perturbation means a small change, a small disturbance, small alteration. Small alteration will be there. Okay, the exact solutions for Schrodinger equation for a determination of discrete energy levels in the bound state and corresponding wave function of square well hydrogen atom harmonic oscillator problem we have already studied. So those systems are called simple systems, but in real we will have only complicated systems. Exact solutions exist only for a few idealized problems. To solve complicated problems, we have to approach some approximation methods. We will get approximate solutions. For example, Zeeman effect, Stark effect, and so on. Even temperature also, phonon also. So those things also will come under perturbation. So perturbation theory, some corrections to the energy. We are going to obtain some energy corrections for the exact one. So that's the idea. For example, what we are going to do is we are going to have the exact solution plus perturbed energy, perturbation energy. We are going to add these two. Exact solution will come under solving Schrodinger equation, correct? Whereas perturbation will come under the expansion series. Okay, expansion series. We are going to add these two and get a total Hamiltonian. So this is our idea. And variation method, as I said, we are going to get psi and E for the ground state, and variation method usually will work out only for the ground state. And for the first excited state, it's okay. Okay. WK method, as I said, we are going to obtain psi and E, and this is a classical method. So semi-classical approach. When H tends to 0 or when lambda tends to 0, we will be getting this WKB method. Okay. So this is a particle in a box which we learned earlier in the first unit. So this is the ideal system in which potential inside the box is 0, correct? Inside the box is 0. For the finite one, potential is constant. Either we have kept potential is 0 or potential is constant. There is no disturbance, and we have obtained psi and E. So this is called unperturbed system. So this is the ideal system. Okay, we can solve Schrodinger equation and exact solution can be obtained for psi and E. Suppose if there is any disturbance, so there is a disturbance, there is a bump in the potential, correct? There is a bump in the potential in the x-axis, so there is a bump. So there is a change in potential, correct? So we cannot apply exactly for the ideal system. So we will have to go with some other approximation method. So there is a bump here. Similarly, bump can also exist on the barrier. Okay, here also bumps. So they are not ideal systems because potential is different. And here also potential is different. Potential is not uniform. Here also in the sliced level, the potential is not uniform. So those systems will have to go only with the approximation methods. So they are called perturbed systems, not perturbed systems, so unperturbed systems. Okay, in unperturbed systems, we will be using only Schrodinger equation. Whereas in perturbed systems, so those are all perturbed systems in which there is a variation in potential energy, potential. Okay, because Hamiltonian consists of kinetic energy plus potential energy. So there is a variation in the potential. So there is a variation in the Hamiltonian. Okay, so those systems are called perturbed systems in which we are not going to use Schrodinger equation. We are not going to use Schrodinger equation and to get the energy eigenvalues. We will be using some expansion theorem. Okay. So as I said, magnetic field and electric field. So those magnetic field, electric field, temperature, phonon, okay, and so on. So they are all perturbing fields. We consider approximate methods that deal with the stationary states. Okay, corresponding to time independent Hamiltonians, which we are going to look into. This will lead to obtain approximate energy values and wave functions. The stationary state perturbation theory concerned with finding the changes in energy levels. Already we have obtained for the exact solution. Will be obtaining. So we have already obtained. We have already obtained the for the models. For example, quantum well models was quantum well, then infinite potential barrier. For all those things we obtained already the energy. These energies will change into either it will go up or down. So there will be change in energy levels. So those levels are called discrete energy levels. bound state. Okay, so there will be change in energy levels and eigenfunctions of a system when a small perturbation is applied. So we'll have to apply only a small perturbation. So the wave mechanical perturbation theory is a simple and beautiful theory developed by Schrödinger, 1926. So Schrödinger himself, he developed this theory, and he has taken from a linear harmonic idea of the string from Newman. He has taken, not from Newman, from Rayleigh. So that's why it is termed as always Rayleigh-Schrödinger time-independent approximation methods. Sometimes it is called as. So he has taken the ideas from linear harmonic, some oscillation of the spring from Raleigh's idea. So earlier Rayleigh solved those oscillations. So that's why it is termed as Rayleigh-Schrödinger time independent perturbation theory. Okay, and also the basic idea is taken from perturbation from classical mechanics. Of course, we always take the frameworks from classical only. For example, in classical physics, we know that the perturbation occurs. For example, so we know the gravity, the attraction between sun and earth, we know already. Suppose there are two planets and there will be attraction, okay, and which follows the equation as F equals G m1 m2 by r square. So we know already this equation. And there are other planets also. So influence of other planets will disturb the attraction of these two forces, correct? These two attractive forces. So what will happen? The planet, either one of the planet will not go with a closed ellipse, but this will have a precession ellipse. So precession ellipse. Okay, because other planets also will have some influence on these two attractive force. Okay, so this will have a precession ellipse. This one is called as a disturbance, perturbation. So they have taken the idea from the classical one. Okay, so the perturbation theory enables us to calculate this change. Similar situation arises in quantum mechanics also, which can be treated with perturbation method. The perturbation theory of two kinds. One is time independent perturbation, another one is time dependent perturbation. In time independent perturbation proposed by Erwin Schrödinger, where the perturbation Hamiltonian is static. Okay, we are going to have only static. Whereas time dependent perturbation, which was proposed by Paul Dirac, which studies the effect of time dependent perturbation on a time independent Hamiltonian, which we will study in the quantum mechanics too later. Okay, in such cases the Hamiltonian may be regarded as broken into two parts, one of which is large and characteristic of a system for which the wave function can be solved exactly, while the other part is small, which can be treated as a perturbation. So total Hamiltonian is divided into two parts. One is unperturbed, another one is perturbed. Unperturbed is exact solution. We will be getting for the unperturbed exact solution. For the perturbed, that we are going to treat as a perturbed term. And this perturbed term should be very, very small. So it's given as very, very small. Consider a physical system which is subject to a perturbation. The effect of this perturbation is shifting the energy levels. We are going to have the shift of energy level will take place. Okay. In fact, the arrangements on energy levels remain the same. So this is what the idea is. We have the total Hamiltonian, which is equal to h0 plus h1. h0 is unperturbed Hamiltonian, for which we have the solution. Apply Schrödinger equation, get the energy eigenvalue, get the wave function. This is okay, and this will be unperturbed Hamiltonian. We are going to add, this will be perturbed Hamiltonian. We are going to add these two. This is your unperturbed Hamiltonian. This is your perturbed Hamiltonian. We are going to add these two. That will be your total Hamiltonian. So perturbed Hamiltonian happens because of the external field. Magnetic field can be magnetic field or electric field, temperature, phonon. So radiation coming out from the universe. So those things are called perturbed Hamiltonian. We are going to add these two. Okay, unperturbed plus perturbed. Oh, total Hamiltonian. And as I said, this will be large and this will be very, very small. So weak potential. We will have to have only weak potential. So h0 represents the unperturbed Hamiltonian, whose energy eigenvalues are known exactly. And we are going to have some approximate methods for this. So h1 corresponds to the perturbed part. Here H1 is very very small, as I said, which compared to H0. So H1 will be very very small compared to H0. H0 is unperturbed. This H1 is perturbed. Now we know already, so as I said, this is for the non-degenerate case. For every wave function, there will be an energy. So we call this as a non-degenerate case. So in this class, we are going to deal only with the non-degenerate case. In the next class, we will be dealing with degenerate cases. Okay, so we know already Schrödinger equation, eigenvalue Schrödinger equation given by H psi equal to E n psi. We know already this. The Hamiltonian is given by kinetic energy plus potential energy. We know already this. So effect on the energy spectrum and eigenfunction will be very very small. Just now we looked into such perturbation is encountered, for instance, in such system subject to weak electric or magnetic fields. So those things are called perturbation. Now we are going to introduce a parameter. This parameter is called the strength of perturbation parameter. So this parameter we are going to introduce in the Hamiltonian. We are going to introduce the new parameter. This parameter is called lambda, is called strength of perturbation. The value of lambda should lie between 0 and 1. Suppose if lambda equal to 0, as I said, lambda lies between 0 and 1. Suppose if lambda equal to 0, these things will get cancelled. It will not be there, correct? It will not be there. We will get only H equals H0. It means that there is no perturbation. Okay? If lambda equals 0, there is no perturbation. So your H equals unperturbed Hamiltonian. H equals H0 itself. Exact solution. Suppose if lambda is exactly equivalent to 1, so we will have maximum perturbation. So lambda should lie between always 0 and 1. What we call this is strength of perturbation. And this equation with the lambda is given by H equals H0 plus lambda H1 plus lambda squared H2. Okay, it goes on. As I said, H0 is large compared to that of H1. The energy associated with the H0 is large compared to the energy associated with H1. So this is unperturbed Hamiltonian. So those things are called perturbed terms. So they are all perturbed terms. So energy, let the energy eigenvalues and eigenfunctions are given by unperturbed terms are given by this and this. Okay, En0, E20 dot En0, because as we said En. Okay, we have written En here, n levels. So similarly, psi 1, psi 2, psi 3 dot psi n, they are all orthonormal wave functions. Okay, orthonormal wave functions. So psi n, En are orthonormal eigenfunctions and eigenvalues of unperturbed Hamiltonian. And for the unperturbed Hamiltonian, the eigenvalue is given by this equation. Okay, for the unperturbed Hamiltonian, the eigenvalue equation is given by this one. H0 unperturbed Hamiltonian acts on psi n0, which is equal to En0 with the psi n0. So En0 denotes the energy of the nth level of the system. Now we will go for perturbed system. Okay, so this is for the perturbed system. H acts on psi n, which is equal to En psi n. And of course we know from this equation total, from the first equation, H equals H0 plus lambda H1. So use just a substitute here. So we will have, instead of H, we will have H0 plus lambda H1 acts on psi n, which will give you En psi n. Okay, it is assumed that it is possible to expand the wave function and eigenvalues of the total Hamiltonian. The eigenvalues and eigenfunctions of the Hamiltonian can be expanded in powers of perturbation lambda. We are going to expand this one. Okay, we are going to expand in terms of lambda. So En becomes your En0 plus in terms of lambda we are going to expand. So lambda En1 lambda square En2. Similarly the wave function psi n equals psi n0 plus in terms of lambda psi n1 plus lambda square psi n2. Okay, here of course lambda 0 is that is 0th power. Okay, lambda to the power 0 is that, so it is 0th power. The power of lambda is the order of perturbation. It's a very important concept. We will look into now. Okay, we are going to determine this and this eigenfunction and eigenvalue. Now we are going to substitute. We are going to substitute these two expressions. We are going to substitute these two expressions in this equation. So you have the previous equation is given, equation 4.7. You are going to substitute 4.8 and 4.9 in 4.7. You substitute. So this expression is like this. Instead of psi n, you can write psi n 0 plus lambda psi n, correct? Plus lambda squared psi n dot dot dot, which is equal to, you have En. En is given by this expression. So En 0 plus lambda En 1 plus lambda squared En 2 dot dot dot, and last one will be your psi n. Psi n, you just substitute the expression for your psi n. Is it okay? 4.10. You substitute 4.9 and 4.8 in 4.7 equation, you will get 4.10, equation 4.10. Now we are going to compare the coefficient. Okay, just to compare the coefficient. First we will compare with lambda to the power 0. Okay, we will compare the first coefficient. So now you just multiply h naught into psi naught. H naught into psi naught. So h naught into h naught operates on psi n 0 will be equal to En 0 that will give you psi n 0. So En psi n 0, correct? H naught, just multiply. First we will multiply. So h naught psi n 0 plus, now we will go for lambda. Okay, h naught lambda psi n. So lambda you pull it out. Okay, here lambda h1 acts on psi n 0, so which is equal to, I have pulled lambda out. Come on, I make it clear. H naught, but just multiply. Okay, operates on this one. So h0 operates on psi n 0, the first one. Second one, h0 operates on lambda psi n 1, lambda h1 acts on psi n 0. You pull lambda out, we will get this. Is okay? For the next one, lambda squared. So h0 acts on lambda squared psi n 2. Okay, this one lambda squared is there. And here lambda h1 acts on lambda psi n, that will give you lambda squared. So you pull lambda squared out. On right hand side, we will have En 0 acts on psi n 0. So En with psi n 0 plus En 0 with lambda psi n 1. Similarly, lambda psi n 1 with psi n 0, you pull lambda out, you will get these two. Okay, simple logic. And next one will be lambda squared. So for lambda squared, you will have to psi n 0 with lambda squared. So we will have En 0 psi n 2. And lambda multiplied by lambda, lambda squared. So we can have again lambda squared is there. So like that we can do. And here also we have lambda squared. Here also lambda squared En acts on psi n 0. See the last one. Now we are going to compare the coefficients. So I said the power of lambda is the order of perturbation. So we are going to compare the coefficients. The power of lambda is the order of perturbation. Okay. So we know that we'll just take the first one. Okay. We'll take the first one. That is h0 acts on psi n 0, which will give you En 0 with psi n 0. We will take the first one. This is for lambda to the power 0. Okay, so we have taken this one. Now we will go for lambda to the power 1. Lambda to the power 1 is this one. So this is equivalent to this. So this is equivalent to this. And this is for lambda to the power 0. So 0th order, correct? 0th order is nothing but unperturbation equation. Unperturbed equation. This is for the first order perturbation, lambda to the power 1. So this is for the first order perturbation equation. Okay.